Good afternoon, everyone. We'll just wait 3 more minutes and then we'll start by 3:05. If there are more people to join, they can join in the meantime. Thank you. Good afternoon, everyone. We'll start the session. So, this is NPTEL's CFD, that is Computational Fluid Dynamics problem solving session. So, the course instructor for this course is Professor Sreenivas Jayanti from the Department of Chemical Engineering, IIT Madras. And I'm if possible, others please mute yourself, like unless you have some questions, so that it will not disturb. So, yeah, so we are now in the week 3 for the problem solving session. In this week, we will solve the problems from past weeks also. So every week, this session is happening mostly on Saturdays from 3 p.m. to 5 p.m. Another one session is handled by another TA also. So if this time is not convenient for you people, you can join in that as well. So similar things would only be discussed between this session and that session, depending on the problems. So we have seen the course layout in the previous classes itself. So right now we have completed week 1 and week 2, where in first week we saw about the calculation of flow in a rectangular duct, and in second week it was about calculation of fluid developed flow in a triangular duct. So this week 3 it was about derivation of equations governing fluid flow, and in week 4 it is equations for incompressible flow and boundary conditions. All these things would be dealt in the coming up weeks. So this is a 12-week course. So the motto behind this problem solving session is to help you people in solving the assignments, and like if there is any doubts regarding the problems, we will be discussing it. So these sessions are being recorded and being uploaded in the YouTube as well. So if those links will be shared by the NPTEL. So if you have any doubts, you can access them afterwards also. So now we'll just go into this week's content. So these problems are somewhat based on the previous 2 weeks assignments as well, for your information. So now we'll see, this is case 1. So we have three figures. So like the problems coming up are based on these 3 figures. So first is a triangle, I mean both are triangular ducts only. So how flow inside them is inside these figures are only asked. Problems are coming up based on these. So questions for this assignment have reference to the following 3 figures. Choose the correct answers from the options given below. So yeah, we'll move to the questions now. In first question, it is asked that you wish to compute the steady laminar fully developed flow field through the triangular duct shown in figure 1. For this case, which of the following is an admissible governing equation? So option 1, it is dou square u by dou x square plus dou square v by dou y square is equal to minus 10. Option 2, it is dou square u by dou x square plus dou square u by dou y square is equal to minus 10. Option 3, it is dou square w by dou x square plus dou square w by dou y square is equal to minus 1 by mu dou p by dou x. So there are 3 equations given, out of which we should find out whether any of them are right or whichever are applicable. For computing the steady laminar fully developed flow field through the triangular duct in figure 1. So in figure 1 it is just a triangular duct. So in this, which is the admissible governing equation of 3, or if it is present over here, that is the question. So options given to find out this are: option A, it is 1, that is only first equation is right. Option B, it is second equation alone is right. Option C, third equation alone is right. Option D, none of the above. So answer is option D, none of the above. Why? Because we'll see. Okay. So we need to compute it in a steady laminar fully developed flow for the flow in a triangular duct. So the triangular plane was in a XY plane. And we need first, before solving any of these, we need to know the continuity equation and the momentum conservation equation for just flow, for studying the flow behavior inside a system. So the continuity equation states that dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. And what does momentum conservation equation gives us? These are for x momentum, y momentum and z momentum. So in x momentum we have rho dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z is equal to minus dou p by dou x plus rho gx plus mu dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. And for y we have rho dou v by dou t plus u dou v by dou x plus v dou v by dou y plus w dou v by dou z is equal to minus dou p by dou y plus rho gy plus mu dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. Similarly, for z momentum, we have rho dou w by dou t plus u dou w by dou x plus v dou w by dou y plus w dou w by dou z is equal to minus dou p by dou z plus rho gz plus mu dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. So now we have a triangular duct. So this is in xy plane. So if the flow is through this plane, the flow would be in the z direction. So right now our consideration is just only w, velocity should only be considered. So steady laminar fully developed flow field through the triangular duct. So here we have a w. W is a function of x and y. Note that it is not a function of z. So we have only the z momentum equation here. Our remaining else should be getting cancelled, because here u v are 0, and so it all the other terms in these particular equations would be vanishing. And we have a assumptions that we are considering only the pressure gradient, and gravitational effects are not considered over here, they are neglected. So what terms would be remaining over here? W is a function of x and y, and u is a 0, v is a 0, and it is a steady state. So this term becomes 0, this u becomes 0, v becomes 0, and w is not a function of z, so LHS side everything becomes 0. And in right hand side we have minus dou p by dou z plus rho gz plus mu dou square w by dou x square plus dou square w by dou y square would be remaining. Dou square w by dou z square would become 0. So this would be the remaining terms, and if we take it, we would be left out with this. Or else if we take dou square w by dou x square plus dou square w by dou y square is equal to minus 1 by mu dou p by dou z is equal to constant after the steady state. This is the equation. But in the options it was given that u is a 0 and v is a 0. So first two equations are not applicable. Whereas in the third equation, why it is not applicable? Because we can see that dou square w by dou x square plus dou square w by dou y square, although this LHS side is a right terms, in the RHS side we have minus 1 by mu dou p by dou x. It should have been dou p by dou z, but since it is that, all three equations are wrong. So the right answer to this particular question is none of the above. So we'll go to question 2. If there is any doubt at any point of time, you can stop and ask, or else at the end also we'll be having a doubt clearing session. So there also it can be clarified. So in question 2, it is about you wish to compute the steady laminar fully developed flow field through the triangular duct shown in figure 1. For this case, which of the following equations is applicable? Similar to the last question, this is asking which of the following equations are applicable for the flow through steady laminar fully developed flow in a triangular duct. So option 1, it is del dot u is equal to 0. Option 2, it is del p is equal to 0. Option 3, it is del dot del p is equal to 0. On looking at it itself, we can say that second one is a false statement, because pressure gradient is a constant. Pressure gradient is not 0. So we'll look at the options that are given. Option A, it is 1 and 2. Option B, it is 2 and 3. Option C, it is 1 and 3. Option D, it is 1, 2 and 3. So first statement is right, third equation is right, but second one is a false. So A is not applicable because it is including 2. B is again not applicable. C is the right answer because it is having 1 and 3 only. Whereas in D it is 1, 2 and 3, because second statement is not second equation is not applicable. This again is a false. So right answer is option C. We'll just look at it more briefly. So continuity equation, it is del dot u is equal to 0. And momentum conservation equation, if we write it in a vector notation, we would be getting this equation. So the left hand side would become 0 and we would be left out with this, and gravitational force would, again we would not be including the effects of it, we would be neglecting because of the assumptions. So, and we would be left out with these two terms. So if it goes, it would be constant, it would not be 0. Delta p is therefore constant and del dot u is equal to 0. If delta p is constant, delta p is equal to 0. So based on these things, 1 and 3 statements are right and it is given by option C. So that is the answer. Now we'll go to question 3. Before that, actually here there is some power fluctuation. So if my connection gets disconnected in between, just wait for 5 minutes. I'll be within that time I'll rejoin the session, so don't leave the session. So now we'll go to question 3. In question 3, it is mentioned that you wish to solve for the velocity field for fully developed through the triangular duct using the grid shown in figure 2. You discretize the governing equations using finite volume method and obtain a set of algebraic equations. How many algebraic equations you will need to solve simultaneously if the walls have zero velocity boundary conditions? So it is what it is asked here. You wish to solve for the flow field for fully developed flow through the triangular duct. So the triangular duct is as shown here. So the gridding is done like this. So here gridding is done like this, and we are discretizing the governing equations using the finite volume method. And after discretization, we are getting a set of algebraic equations. So how many algebraic equations we will be needing? We needed to solve simultaneously if the walls have zero velocity boundary conditions. So we look at the options. Option 1 it is 3. Option B it is option A it is 3. Option B it is 6. Option C it is 10. Option D it is more than 12. So if we look at it, we can see that for every cell we would be writing a discretized governing equation in the finite volume method. So how many cells are we having here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the answer to this problem is 10 equations. Even though the wall boundary condition is given as zero velocity, we would be for each cell we would be having an equation, and it would account to 10 equations. So answer to this problem is option C, 10. So we'll just see how we can discretize it based on the finite volume method. So what is finite volume method? Here we would be using the direction, cosines and gradients. So the finite volume method discretization is based on direction, cosines and the gradients. So the direction cosines are outward normal for each side. So we are evaluating at each side. Whereas for the gradient outward normal for the each side, so the gradients are evaluated at midpoints of each side using values of the cell and those of neighboring cells or the boundary conditions. So for example, consider this. So direction cosines would be outward normal for each side, and for all sides we would need to be summing up, and gradients are evaluated at midpoints of each cells from this cell under consideration and those of the neighboring cells of the boundary conditions. So it can be from here to here or from boundary conditions, whichever is applicable. So how would we denote the finite volume method? We would be using this approach. So where integral of n dot del w is dl is equal to summation of n dot del w into iji is equal to cai. So like here we are multiplying by length. It should have been L. So if we put it in a more elaborate manner, what we would be getting, if it is a consider if it is a triangle, we would be having nx dou w by dou x plus ny dou w by dou y at AB side and into length of AB, and nx dou w by dou x plus ny dou w by dou y into at BC and into the side length of that side BC plus nx dou w by dou x plus ny dou w by dou y at side CA into LCA is equal to CABC. That is area of the triangle, or whatever the, this particular is an expansion of the triangle. So here we are having the area. So for this particular question, we are using this particular grid. So we'll use this and we'll see how we can discretize it. So this is the discretized, this is the geometry given triangular duct. So we have 10 cells in this particular geometry, and we need to use the finite volume approach to get the discretized equations. So the thing to be noted is, for each of these grids, we need to know the centroid, because we are calculating from the midpoint to the midpoint of the adjacent cells for the gradient calculation. So first we need to know the centroid of the triangle is given by x1 plus x2 plus x3 by 3 plus for the x coordinates, and for the y coordinates we have y1 plus y2 plus y3 by 3. Whereas for the centroid of the rectangle it would be x1 plus x2 by 2 plus and for the y coordinates we have y1 plus y2 by 2. So for the simplicity of this particular problem, solving this problem, what are we doing? We are taking it to be considering of 8 units in dimension in the x-axis and 8 units in the dimension in the y-axis. So here we have, we are putting points as 0, 0, and for each cell we are giving 2 dimensions, 2 unit dimensions. 0, 0, 2, 0, 4, 0, 6, 0, 8, 0, and similarly in the y-axis we have 0, 2, 0, 4, 0, 6, 0, 8. These coordinates are just mentioned for the ease of calculating. And 1, 2, 3, 4, like similarly we have mentioned the coordinates of the vertices of the each particular cell. So after this, what are we going to do? We are going to do the centroid calculation. So for simplicity, like for our understanding right now, we'll just keep it over here. We'll just see for 7 cells. After that we'll go to it. So in the first cell it is about 0, 0 to 2, 0. And 0, 2 to 2, 2. So what would be the centroid of the x coordinates? It would be 1, 1, and y coordinate again would be 1 because we are going from 0 to 2 and 0 to 2 in the y axis as well. For second cell we are going from 2 to 4, so it would be 3, 1, and it is 4 to 6, so it would be 5, 1. Whereas okay, let us now look into the 7th cell, or else since we have now seen about 3 cells, we will just use this to look into the remaining cells. So in the 4th cell, what are we having? 6, 8, 6, 0, 8, 0 and 6, 2 are the coordinates of that particular triangle. So for the 4th cell, how are we going to find the centroid? We are going to use the 6.6667 because 6 plus 8 plus 6 divided by 3. So 14, 20 divided by 3 is 6.6667. That is the coordinate, centroid coordinate for the x-axis. I mean x coordinate for the centroid. And for the y coordinate, how would we find? It would be 0 plus 0 plus 2, that is 2 divided by 3. So what is x, like triangular? For triangle, the coordinate centroid is obtained by summing up the coordinates and dividing by 3. So it is 2 by 3, it is 0.667. So again coming back, it is the 5th cell is a square. So it would be 1 comma, it would be 1 in the x direction, and in y direction it is 3. So it is 1 comma 3. And in 6th cell we have 2, 3. So it would be 3 comma 3. So in a similar fashion, we have calculated the centroids for all these particular cells. So for the 10 cells, we have calculated the centroid. And in the last cell, how are we doing? It is 0 plus 2 plus 0 divided by 3, that is 0.6667 in the x. And for the y, we have 8 plus 6 plus 6, that is 20 divided by 3, it is 6.67. So initial step, we have calculated the centroid for the all particular cells. So after the centroid calculation, now we are going to write the discretized equation for all individual cells. So now we are starting with cell 1. So this is cell 1. Remember that is 0, 0, 2, 0, 2, 2, 0, 2. So it is 0, 0, 2, 0, 2, 2, 0, 2. This is cell 1. So now what did we see about in the finite volume approach? We need to multiply the direction cosine with the velocity gradient, and the sum would be equal to the area a times some constant. So right now we'll write the direction cosine times the velocity gradient. So let us take this first cell, and it is what also how are we calculating the velocity, like the gradients? We are calculating from the midpoint of the cell to the next adjacent cells or the center of the each face. So that centroid is useful over here. So this is like this direction is -1. So -1 into this is cell 1, right? So it is 0, 2. So the midpoint is W1. So W1 uh, or the cell 1, W1 minus this is velocity at the W1, and this at we are stopping over here because next to it in the left hand side we are not having any particular cells. So W1 minus 0, and so W1 minus 0 by divided by what is the centroid point? It is 1, and we are stopping at the walls. So it is 1 minus 0. And if we are looking at this direction, so we are again going from first cell to second cell. So it would be W2 minus 1, and what would be the centroid of this particular cell? That is 3. So 3 minus 1, because the centroid is 1 over here and centroid is 3 over here. So like if we are having two particular cells, so it is 0. If we are taking x coordinate alone, it is 4, and midpoint would be 1, and here the midpoint would be 3. Velocity wise, it is W1 inside cell 1 and W2 inside cell 2, and wall velocity is given as 0. So now I think you can clearly understand it is W1 minus 0 divided by 1 minus 0, and similarly W2 minus W1 divided by 3 minus 1. Similarly, what other cells on top? We have one more cell, right? So 1, 2, 3, 4, we have fifth cell over here. This would be W1. So, and this would be W5, right? W5. So what are we having here? W5 minus W1, and here we have 0, 2 and 4 in the y-axis. So the mid centroid is 3. 3 minus 1. So W5 minus W1 divided by 3 minus 1 into, it is in the positive direction. So we are having positive 1. So the direction cosines are outward normal for that. And then we have W5 minus W1, and then we have one more thing, W1 minus 0. So W1 minus 0 and 1 minus 0. So here we are stopping at the boundary. So 1 minus 0 times minus 1 is equal to C into A1. So area is like 2 into 2 because it is a square. So it is 4. Now so on the basis of that, we are calculating the values. I mean, we are discretizing using the finite volume approach, and we are getting this equation. So on simplifying this, we are having values for the velocity, and we are having some coefficients, and this is the equation we are getting for the cell 1. Like we are just simplifying it, and on further simplification, this is the equation 1 which we are getting from cell 1. Similarly, for cell 2, we need to do the calculation, and cell 2 the calculation is like like we'll go from this -1. So here cell 1 is here and cell 2 is here. So W2 minus W1 and 3 minus 1. So we are, how are we dealing? Like more precisely, if we go back, it is like W2 minus W1 and centroid is 3 minus 1, and W6 minus W2 and centroid is 3 minus 1. So W2 minus W1, and it is 3 minus 1 in the this direction. And if we are going with this direction, what would be having? It is W3 minus W2, and it is centroid is 3 here and centroid is 5 there. So 5 minus 3. And it is for Y we have W1, 2, 3, 4 and 5, 6. So sixth cell is immediately above it. So W6 minus W2 minus divided by, so here it is 1, so there would be 3. Centroid is 3 minus 1. So W6 minus W2 by 3 minus 1, and immediately after that we have a -1. So it is W2 minus 0 because it is given that wall velocity of the wall is 0. The boundary condition is velocity wall velocity is 0. So W2 minus 0 and it is 1 minus 0 is equal to CA2. We are again simplifying the equations and we are getting one more equations. So till now we have solved for two cells and we have got two equations. Similarly, we are going with third cell as well, and the equation is similar, like it would be minus 1, which is W3 minus W2 divided by 5 minus 3, and in x-axis we would be having W4 minus W3 and divided by the centroid of this triangle is 6.6667 minus 5. We have calculated the centroid previously itself, so we are calculating the midpoint. I mean, we are calculating is from the midpoint of the adjacent cell to this particular cell. So 6.6667 minus 5, and top way we have okay. Okay, immediately above it also we have a triangle because above third cell we have this seventh cell. So what is the centroid of the seventh cell? It is 4.67 by 2.67. 2.67 is the y. So 2.67 minus 1, W7, seventh cell is there, minus W3, and it is at the bottom for this particular direction, particular edge, we have W3 minus 0, we are stopping at the edge, by 1 minus 0, and it equal to C into A3, and A3 is again 2 cross 2 because that is the area of the cell, it is 2 cross 2, and now simplifying we get this equation. Cell 4 is a little complicated because we have a triangle. So in the this particular direction and this particular direction we can resolve because it is minus 1 and it is W4 minus W3 and centroid is 6.667 minus 5, and this particular down direction it is minus 1 into W4 minus 0, centroid is 0.67 divided minus 0. But for this particular side, how are we going to resolve? Since it is outward normal is in this direction, we need to resolve it into x and y coordinates. So we are projecting it and we are using this. So this would be one and this would be another one. So it would be 90 degree and it should be casting a 40. I mean, it would be separately it would be 45 degree. So cos 45 or sin 45 would be 0. So we are getting this particular value as 1 by root 2 and this as 1 by root 2. And W4, this is W4. Again when we go from here, from this to this wall becomes wall boundary condition. So W4 minus 0, and from here to here as also we get W4 minus 0. But for the gradient, that is delta x and delta y, we have 6.6667 minus 7 because it would be like center would be 7 and it would be 1. So 0.667 in cross 1. So it would be 1 in the middle and 1, this midpoint would be 7 cross 1 of that particular side. So we are, after simplification we are getting this, and for the area we would be having half into base into height. So half into 2 into 2 would give us 2. So this is how we resolve for the cell 4. We discretize for the cell 4. And after cell 4 we are going to cell 5. Cell 5 again is a simple one because it is again a square cell. And we are having this equations. So cell 5 it is at the second row. 1, 2, 3, 4 cells we have covered in the first row and cell 5 is in the immediately above cell 1. So here again we have a wall boundary condition for this particular side. So now we are going for the y direction. So it is W5 minus W1 times minus 1 divided by 3 minus 1. and it is W5, and this side it is W6 minus W5 and divided by 3 minus 1, and it is W5, 6, 7, and immediately above it is 8th cell. So W8 minus W5 divided by what would be it? 2, 4 and 6. So it would be 5 minus 3. 5 minus 3, and we are now coming to this direction. It is W5 minus 0. So it is 1 comma 1 minus 0. So again, area of the cell we would be calculating it as 4C, and after that we get the simplified equation. So similar approach is used for cell 6 as well. Cell 6 is above second cell, and left to it we have fifth cell, and right to it we have a seventh cell, which is a triangle cell. So here we need to, for this side would be like we can see that W6 minus W2 minus divided by 3 minus 1. And this side we have W7 minus W6 divided by 3 minus 4.667. So W6 minus W7 or W7 minus W6, whichever is convenient. W6 minus W7 divided by 3. So next is a triangle. So triangle centroid is 4.67. And again here immediately above that even we have a triangle, because 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is 9th cell. W6 minus W9, 3 minus 4.67. And to this we have W6 minus W5, and it is 3 minus 1 is the centroid. So we are having one more equation which on simplification looks like this. So now we are left with 4 more cells. So in cell 7 it is a triangle cell. So for triangular discretization, what we are doing, we are using this. So this again is a simple, and this again is a simple. For this again the outward normal looks like this, and so we need to resolve it into nx, x and y components. So again we are using the 45 degree, and the equations would be 1 by root 2, 1 by root 2. I mean the values would be 1 by root 2 and 1 by root 2. How we are getting that 1 by root 2, 1 by root 2 and all, I think you would be knowing how to calculate the direction cosines. If not, there is one more problem in the coming up, so you can get it over there. And this is seventh cell. So this is midpoint is what would be 4 and 2 it is, so it is 3 and 5 comma 3. So we'll just see how we are resolving this and this alone. So this is 1 by root 2. Above that we do not have anything, so it is W7 minus 0, and we are centroid is 4.67. okay, in this it is 2.67. in the y direction if you look, it is 2.67 minus 3, so the midpoint is 3. So 2.67 minus 3, that is at the edge or the side, midpoint of the side, because above, after that the triangular duct is ending. So 2.67 minus 3, W7 minus 0 divided by 2.67 minus 3 into 1 by root 2. Similarly for the x we have W 4.67 minus 5, and it is W7 minus 0. So in the wall it is mentioned that velocity is 0 at the walls. So for the simplification gives us this values. A7 is the area of the cell, that is half into base into height, and we are getting this values. So 8th cell we are having it as this. So in 8th cell again we need to discretize it. So it is center to the 1, 2, 8th cell, it's at the top of 5th cell, and left side of the 9th cell. So here what we are doing, W8 minus W5 divided by 5 minus 3. So 8 minus 5, 5 minus 3, and 8 minus 9, and 9 is a triangular cell, so it is 2.67, and here it is 1, and it is again 8 to 10, 10th cell again is a triangular cell, so it is 5 minus 6, 7, 6.67, so minus 1, and this is similar. So it might look like I am rushing, but once I'll show back, that time I think it would be more clear. And we are getting one more equation, and cell 9 and 10 is triangular cells. So it adjacent to ninth cell is eighth cell, and bottom of it we have I think sixth cell. So W9 minus W6 and W9 minus W8. These are normal cells, and this for okay, these are these are normal cells, and we are again dissolving 45 degree, and because the outward normal is in this direction, nx and ny components we are getting, and we are using the ball boundary condition as 0, that is W9 minus 0 and W9 minus 0. So it is, what is it, 2.67, and here it is 4.67. So 2.67 minus 3, 3 is the midpoint, and 4.67 minus 5, because 5 is the midpoint. What is the midpoint? That is 3 comma 5. That is, this point is 3 comma 5. So we are calculating from there to there. And see A9. So we are just calculating for each side the values, or we are discretizing the using the finite volume approach the each sides, and we are using it to equate to area of the cell times some constant. So we are getting one more equation, and cell 10th cell is the topmost cell, and its midpoint in this point would be 6 8, and it would be 1 comma 7. So you can see that 7 comma 1, 7 and 1 are used over here, and centroid is 0.67 comma 6.67. So 0.67, 6.61, these are for y and x resolved components, and these are for this side and that side. We are again calculating minus 1, minus 1, and on simplifying it, we are further getting one more equation. So right now we have discretized the 10 equations in 10 cells, and we have got 10 equations. So these are those 10 equations. Each equation is obtained from that particular cell. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 equations. So this was a question asked in the question 3. How many equations, algebraic equations, will you need to solve simultaneously if the walls have zero velocity boundary conditions? So if we need to solve these if we need to solve this particular triangular grid, so we need to solve the 10 equations. C is equal to 10. I mean, C 10 is the right answer. So we need to solve 10 equations. So how are we doing? We are using the finite volume approach because it was asked in the question. And for finite volume approach, we need two things. The first one is the direction cosine, and the second one is gradients. So because this is the approach, here we can see that we are, for each side, we are using multiplying the gradient with the direction cosine and multiplying with the length of that particular side. So for this we have found out the centroid, and for this for each geometry, each cell geometry, and after that we have discretized it in almost all the cells for the direction cosine and the values, and we have taken it as a constant, and we have used. So in all these things, one more thing is I haven't multiplied by 2 because 2 is the length of those particular sides, so which would not be an issue because all sides are 2. So on dividing, though, like, all the equations would give us 2 because we have introduced a constant in the RHS side. However, that constant would be varying, but it should have been multiplied by the length of that side, which I haven't done. So that's okay. For each side, we have calculated the direction cosine and the gradients, and it should have been multiplied by the length of that side, which I haven't done. But in this particular case, we are not going with finding any particular value, so it would not be an issue. Just with conceptual understanding we are doing, and so it is fine. And however, it would be adjusted in the RHS side. So, and then we are resolving for the triangles, we are resolving it into the x and y direction cosine, because the outward normal is in some 45-degree angles, because it is an isosceles triangle. So we are getting 10 equations from the 10 cells. These are those 10 equations. So yeah, so I think it is clear now. Based on this equations, we are having some few more questions as well. So now we'll go and check out those questions. Question 4. In question 4, it is mentioned that for the grid shown in figure 2, if the algebraic equations resulting from the discretization of the governing equations are arranged in the form of a matrix equation, then the non-zero coefficients in the coefficient matrix will. So what is asked for the grid shown in figure 2? Figure 2 was the grid we have solved right now. So if the algebraic equations resulting from the discretization of the governing equation, so we have got 10 algebraic equations, right? If they are arranged in the form of a matrix equation, then the non-zero coefficients in the coefficient matrix they will not have a diagonal structure. They have a tridiagonal structure with 3 adjacent diagonals including the main diagonal. Have a pentadiagonal structure with 5 adjacent diagonals including the main diagonal. Have a pentadiagonal structure with 0 diagonals in between some of the non-zero diagonals. So what is asked? We have got 10 equations. So if we are arranging it in the matrix form, so in the form of AW is equal to C, so the coefficient matrix would be A. So what sort of structure would that particular matrix have? Would it be having a diagonal structure, or would it not have a diagonal structure, or some things like tridiagonal or pentadiagonal structure can be observed, is asked in the question. So for that we need to just look at the equations once. So these are the equations. If we look, just we need to arrange it in the matrix form, and we need to identify if it is forming any diagonal structure. But on looking, we can say that it is not forming any diagonal structure apart from the one diagonal that is present, so which should be obviously present for solving, unless we don't have any solution also. So it is not having any diagonal structure is the answer. So we will just put it in the diagonal form, and then we can say, but answer to this question is it would not be having any diagonal structure. So this is we are arranging the equation as this form: AW is equal to C, where W is a vector matrix from W1 to W10, because for each cells we have put one equation, and this is the constant. Again here it would be varying because I haven't multiplied by the length of the side. AW is equal to C. So here we can, here we can see that only the diagonal structure is remaining. This is a square matrix, right? But on looking at it, we can say only this diagonal is present. Apart from that, we are not able to see a tridiagonal because here we have some zeros. Similarly, above also we do not have anything, and there are so many zeros. So in this particular question, it is asked that whether it is forming any diagonal structure. It does not have a diagonal structure. Option B, it is having a tridiagonal structure with 3 adjacent diagonals including the main diagonal, which is false. And option C, it is have a pentadiagonal structure with 5 adjacent diagonals including the main diagonal. Again, it is a false. Have a pentadiagonal structure with 0 diagonals in between some of the non-zero diagonals. Okay, here it is has mentioned that it has a pentadiagonal structure where some 0 diagonals are also present in between non-zero diagonals. Again, it is not the case because we are not able to find out any diagonals in this particular. Like only the main diagonal is present. Apart from that, there are so many zeros through which we are not able to have any diagonal structure. So answer is option A, which means that it does not have a diagonal structure. Now we'll go to question 5. In question 5, it is asked that for the grid shown in figure 2, if the algebraic equations resulting from the discretization of the governing equation are arranged in the form of a matrix equation, then the number of rows having exactly 3 non-zero coefficients in the coefficient matrix is. So, what is asked, if the algebraic equations resulting from the discretization of the governing equation are arranged in the form of a matrix equation, then the number of rows having exactly 3 non-zero coefficients in the coefficient matrix is. So, similar to that problem, we have arranged it in the governing, we have arranged it in the matrix form, that is AW is equal to C, where A is a coefficient matrix. So in this question it is asked that how many rows in the coefficient matrix is having exactly 3 non-zero coefficients. So it is exactly 3, so which means that it must have only 3 non-zero coefficients. So option A it is 2, option B it is 3, option C it is 5, option D it is 7. So answer is actually option B. We'll just go back and count actually, because we can see that this is the coefficient matrix. In this first row we have 1, 2 and 3. 3 non-zero coefficients are there in first row. In second row 1, 2, 3, 4 we have 4 non-zero coefficients are there. Third row we have 1, 2, 3, 4 non-zero coefficients. In fourth row we have 2 non-zero coefficients. Fifth one we have 4 non-zero coefficients, 1, 2, 3 and 4. And again for the sixth row we have 1, 2, 3, 4 and 5 non-zero coefficients. In the seventh one we have 1, 2 and 3 non-zero coefficients. Eighth we have again 4, ninth we have 3 and 10th we have 2. So in the question it was asked that how many rows are having exactly 3 non-zero coefficients. So the keyword here is exactly 3. So the right answer is the row number 1, row number 7, row number 9 are having exactly 3 non-zero coefficients. So it is 3. Answer is 3. Option B, that is 3 is the right answer. Yeah, we'll go to question 6. In question 6 it is asked that for the grid shown in figure 2, if the algebraic equations, for the grid shown in figure 2, if the algebraic equations resulting from the discretization of the governing equation are arranged in the form of matrix equation, do you expect the diagonal dominance condition will be satisfied? So for the grid shown in figure 2, for the figure 2 is nothing but what we discretized right now. So if the algebraic equations resulting from the discretization of the governing equations, so we have got 10 algebraic equations from the discretization. For if we are arranging it in the form of a matrix equation, what do we expect? Do we expect it the diagonal dominance conditions will be satisfied? So that is the question. So if we have got 10 equations from the discretization of the governing equations from the particular geometry and for particular grid structures, so what would be the diagonal dominance condition? So option A it is yes, the equation can be ordered in such a way that the diagonal dominance conditions will be satisfied. Option B, no, the diagonal dominance conditions cannot be satisfied no matter what how the equations are ordered. Option C, we cannot say a priori about the diagonal dominance condition. Option D, diagonal dominance condition is irrelevant for unstructured grids. So the answer is actually option A, because the equations can be ordered in such a way that the diagonal dominance conditions will be satisfied. What is diagonal dominance? Diagonal dominance is nothing but the absolute value of the diagonal elements would be greater than or equal to the sum of the other elements present in the particular row. The diagonal dominance should be satisfied when the diagonal elements, absolute value of the diagonal elements would be greater than the sum of the absolute values of the other particular elements in that particular row. So for example, if we are taking row 1, the particular value in the diagonal, that is 1 comma 1, or should be greater, that absolute value should be greater than the sum of all the other elements present in that particular row. So when we look back in the matrix, we can see that the diagonal elements are the greatest in the are the greatest. The absolute value of the diagonal elements are the greatest because point 0.5 plus 1, point 0.5 is 1 where 3 is greater. Point 0.5, point 0.5 again 2.5 is greater. Again if we add all the other elements also we get 2.7 is greater. Similarly we have on every equation it can be found that the diagonal element is absolute value of the diagonal element is greater than the sum of the all other elements. So we expect the equations can be ordered in such a way the diagonal dominance conditions will be satisfied. So the equation can be ordered in such a manner also. So that option A is the right answer. Option B, it states that no diagonal dominance cannot be satisfied no matter how the equations are ordered. It is false. We cannot say a priori about the diagonal dominance condition. Again, it is false. Diagonal dominance is irrelevant. No, it is again false. So answer to this particular question is option A. Option A is the right answer. Now we'll go to question 7. In question 7, it is asked that if the shaded triangle in figure 3 is a right angled isosceles triangle, then the direction cosines nx and ny of the vertical side are. So what is asked? If the shaded triangle in figure 3, this is figure 3, is a right angled isosceles triangle, then the direction cosines nx and ny of the vertical side are. So okay, this is the shaded triangle. So this is a right angled isosceles triangle. So the other two angles must be 45 each, because sum of the angles in a triangle is 180 degree, and since it is mentioned right angled isosceles triangle, other two are 45 each. Then the direction cosines nx and ny of the vertical side are. So it is this way. What is direction cosine? It is the outward normal from the particular side. So in this way we can see that it is minus 1 0. 1 comma 0 it is false because it is in this direction, or else 0 comma 1 again it is false, minus 1 comma 0 again it is false, it is 0 comma minus 1. So we can also say that it is making this particular ray is making 90 degree with the y axis, and it is making like 0 degree or this way. If it had been in that way, it would have been 0 degree. So direction cosine is the angle that particular vector is making with the particular axis. So nx is the angle of that vector. It is making direction cosine. I mean cosine of that angle it makes with that that side. So this is the vertical side. So here we can see that it is making 90 degree. So what is with the y axis? So ny is cos 90 degree. So it is 0. So either option A is right or option C is right. And we can see that it is going this, I mean it is making 180 degree with the x, or so it is minus 1 is the right answer. So it is minus 1 comma 0. Option C is the right answer. Now we'll go to question 8. In question 8 it is asked that if the starred triangle in figure 3 is a right angled isosceles triangle with a vertical side of length A and horizontal side of length B, then the direction cosines of the diagonal side are. So this particular problem is again similar to the last question in regards with the figure 3. So what would be the direction cosines of the diagonal side? So last question it was about the vertical side. Here it is about the diagonal side. So option 8 is a by root of a square plus b square, comma b by root of a square plus b square, Option B, it is minus a by root of a square plus b square plus b by root of a square plus b square. Option C, it is minus b by root of a square plus b square plus a by root of a square plus b square. Option D, it is plus b by root of a square plus b square by plus a by root of a square plus b square. So for that we need to first get the triangle and we'll see the answer. I think it's option D is the answer. We'll just see. So it is that particular triangle. So what have we done? This is the figure 3. So we are dealing with this shaded triangle. If the star triangle or okay, star triangle is this one. So this is this triangle is the right angle isosceles triangle with a vertical side of length A and horizontal side of length B. So vertical side is length A, horizontal side is length B. So this is the diagonal side. Direction cosines of the diagonal side. So directional cosine would be, it would be the outward normal from this side would be this. So this we need to resolve into x and y. So how if we this take this as a right angled isosceles triangle, we have this as 90 degree, and since it is like we can see that it is a part of the side is part of the original triangle, so it is a right angle isosceles triangle as well. Right angle isosceles triangle with vertical side is A and horizontal side is B. So AB we have taken as A and BC we have taken, sorry, it is BC. So AB we have taken as A and BC we have taken as B. So this is 45 degree and this is 45 degree. So we need like again this would be 45 degree, 45 degree. So we need to find the diagonal's length first. So by Pythagoras theorem, we know that it is square root of a square plus b square because it is a right angle triangle. That would be a square plus b square. So I mean this would be a and that would be b, and this particular length is a square plus b square. So nx now we need to find. So where is it? This is nx. So this is making 45 degree and this as well as making 45 degree. So this is like with respect to b. So it is would be b by a square root of a square by b square is the x cosine, sorry, nx direction cosine in the x direction. So nx is equal to 45 cos 45 degree. So it will be b by root of a square by b square, and ny would be this way. It would be again a by, if we take it in this direction, it is a by root of a square by b square. So answer is b by root of a square by b square plus comma a by root of a square plus b square. That is option D is the right answer. So we have just discretized it into it and we have found the answer. And now we'll go to question 9. In question 9 it is asked that in deriving the set of algebraic equations for the grid shown in figure 3, boundary conditions are not used for how many cells? So first it is asked that we have taken the figure 3 and it is in deriving the set of algebraic conditions for the grid shown in figure 3, boundary conditions are not used for how many cells? So option A it is 1, option B it is 4, option C it is 7, option D it is 16. So first we will look at what is figure 3, and it is option C actually. So this is figure 3. So it is question is about boundary conditions are not used for how many cells. So whatever the cells are not coming under the influence of boundary, we would not be using, because in the first question it was asked that wall boundary condition was given. Wall boundary condition states that velocity at the walls is 0. So similar to that, any conditions could be put it in the boundary. Apart from that, we need to count how many cells are remaining. So if we take the total number of cells, we would be having 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. There are 16 cells which are used. If we discretize it, we would be getting 16 number of equations, and which can be, I mean, we would be getting 16 algebraic equations from the finite volume method or so. But it is not about getting how many number of equations, because similar question was we have seen in the previous class, I think. So it is about in deriving the set of algebraic equations, boundary conditions are not used for how many cells. So it is which are not coming under the influence of boundary, this is not coming, because we are in finite volume approach, we were just dealing with the influence of cell values and all boundary conditions. So we are not using in cell 1, and in cell 2 as well, cell 3 again this comes under the influence of boundary, and cell 4, cell 5, cell 6 and cell 7. So in these particular cells, these many cells, we are not using the boundary conditions. So in question 9, it is about in deriving the set of algebraic equations for the grid shown in figure 3. Boundary conditions are not used for how many cells? We have not used the boundary conditions in 7 cells. Okay, we'll just take a quick 5 minutes break and then we'll resume the session. We'll start by 4:14. I think it is 4:09 now. We'll start by 4:14. These are the, I mean, till now we have covered almost all the big problems. Hereafter, some few conceptual problems will be coming, which we will be looking at. Before that, let us take a 5 minutes break and then we'll come back sharp by 4:14. let us get back to the session. Just a quick actually thing. I might have faced an power interruption in the next 15 minutes or so. I'll immediately rejoin the session, but uh, like from other source. So if there is anything, just don't mind. We'll, yeah, thank you. In question 10, it is about comparing the finite difference method and finite volume method for fluid flow problems. Which of the statement is true? So we are comparing finite difference and the finite volume method for the fluid flow problems. So which statement is true? Both methods would give the same result for very fine grids. For simple geometries, finite difference is preferable. FD is preferable for complex geometries. And options, these are three statements. We need to identify which of the following statement is right. So in option A it is 1 only, option B it is 2 only, option 3 it is, option C it is 1 and 2, option D it is 1 and 3. So answer is option C. Because finite difference and finite volume method, when comparing at final grid levels, both the methods would be giving the same level of accuracy, same results. It should not be varying because the grids are already finite, so it would be the same. So we'll just see what is the issue with these three statements. The first statement, both methods would give the same result. That is true. I mean, for very fine grids, the thing is, for very fine grids, the results would be same. Otherwise, it would be, difference would be there. And for simple geometries, because the since CFD, it is about information passing from one grid to another. So if the grid size is very fine, the thing would be the same, right? Otherwise, it depends on the method and depends on the accuracy and order of the equations. Everything would be influencing. But for very fine grids, both methods would be giving the same results. Second statement, for simple geometries, FD is preferable. So if you remember what FD is, it is about finite difference approach, where we are discretizing the equations into the grids by using central differencing schemes, forward differencing schemes, backward. Like similarly, we have used the schemes from one grid to another, where it can be mentioned in as I plus or minus, x plus or minus I, y plus or minus I, similar to that. If we can define it, it would be better. So for simple geometries, FD is preferable, finite difference is preferable. But for the y, if FD method is the easier method of the two, so why not we go for all the geometries? The disadvantage is it cannot be used with the complex geometries. So third statement is a false statement, because it is not preferable for complex geometries. Rather, it is statement is wrong. Rather, it is not preferable, and we go with finite volume or finite element method depending on the application required. So 1 and 2 are the only right statements. So option A, it is 1 only, option B, it is 2 only, whereas option C, it is 1 and 2. So right answer to this particular problem is option C. We'll go to question 11. In question 11, it asks that choose the correct answers from the options given below. Identify all the correct answers. Newtonian fluid assumption is quite accurate for option A, air, option B, water, option C, crude oil, option D, diesel. Okay. So what is Newtonian fluid? Newtonian fluids are those fluids which obey the Newton's law of viscosity. So in this, shear stress is directly proportional to the shear strain. Thereby, viscosity would be constant and at that particular temperature. So, Newton fluid assumption is quite accurate for air, which is true. Water, again true. Crude oil, it is false. Diesel is true. So we'll see the answer. Answer is A, B and D. Why crude oil is not obeying Newton's law, Newton is not coming under Newtonian fluid? Because it is a non-Newtonian fluid, because its shear stress and strain relation would be different. I think my connection got interrupted. Just a minute. I am audible right now? Okay, if there is any
Yeah, you are audible.
yeah, okay, thank you. Okay, now we'll just continue. So, yeah, crude oil, it would be having few particles present in it along with other things like wax, paraffins. Those things would be accounting to the fact that stress is not, the stress is not directly proportional to the shear rate. So, it would not be coming under the Newtonian fluid. It would be coming under the non-Newtonian fluid. So, option C alone is a false. That could not be accurate for the accurately holding the Newtonian fluid assumption. So option A, B and D are the right answers. We'll go to question 12. In question 12, it is mentioned that the advection term in the momentum conservation equation in the x direction for constant property two-dimensional Newtonian fluid can be written as. So what is asked? The thing is, fluid is a Newtonian fluid in this case, and we are asking for the x direction, and it is a constant property. So density is constant, and it is two-dimensional Newtonian fluid. So it is written in a two-dimensional form. So what is the answer? Option A, it is u dou u by dou x plus u dou v by dou y. Option B, it is u dou v by dou x plus v dou u by dou y. Option C, it is u dou u by dou x plus v dou u by dou y. Option D, it is u dou u by dou x. So here what is asked? We are asked to write for the x direction momentum conservation equation the advection term. Advection term is nothing but in the what is in the accounting the momentum transfer due to advection, that is in the LHS side. What the thing comes in the LHS side is accounted here. So since it is in the x direction and it is two dimensional, we are having u dou u by dou x plus v dou u by dou y. Because it is x direction, we are having it as u, and therefore option C is the right answer. We'll see what is the governing equations. We have continuity equation and the momentum equation. We have three. Actually, I have written for the three-dimensional case. This is x momentum conservation equation, y momentum and z momentum. But for the two-dimensional case, the z term would be going off, and here this is the advection term. So for x direction, what are we left with? U dou u by dou x plus v dou u by dou y. Okay. Okay, actually I didn't notice. I'm sorry. Like, we'll just go back and see. Actually, question 11 we have finished. Air, water, and diesel. And in question 12, it is about advection term in the momentum conservation equation in the x direction for constant property two-dimensional Newtonian fluid can be written as u dou u by dou x plus u dou v by dou y, b u dou v by dou x plus v dou u by dou y, c u dou u by dou x plus v dou u by dou y, and c it is u dou u by dou x. So answer is option C, u dou u by dou x plus v dou u by dou y. So for that, we just look at the governing equations. This is continuity equation and this is momentum equation. So in this particular slide, I have given for the three-dimensional case, but in the question it is asked for two-dimensional case, and that too for the x direction. So this is for the x momentum, y momentum, and z momentum conservation equations. So we'll just take the advective terms. Advective terms include these: u dou u by dou x plus v dou u by dou y plus w dou u by dou z. So since it is not for three-dimensional case, we are left with u dou u by dou x plus v dou u by dou y is the right answer. So on going back the slide, u dou u by dou x plus v dou u by dou y is the advection term in the momentum conservation equation in the x direction for constant property, that is density is constant, two-dimensional Newtonian fluid. And answer is option C. And we'll go to question 13. In question 13, it is asked that diffusion term in the two-dimensional y momentum conservation equation is given by mu dou square v by dou x square plus dou square v by dou y square, mu dou square u by dou y square plus dou square u by dou y square. Option C, it is mu dou square v by dou x square plus dou square u by dou y square. Option C, it is mu dou square v by dou y square. Answer to this is actually A, because we are dealing with two-dimensional case. Yeah, answer is A. Because we are dealing with the two-dimensional case and we are asked to find the momentum conservation equation in the for the y momentum conservation equation. So if we go back and look at the previous equation itself, I mean the governing equation slide, we can see that for the y momentum direction, this is the equation and this is the terms. So diffusion term, so mu dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. Again we are neglecting this because we are only looking at the two-dimensional case. So mu times of dou square v by dou x square plus dou square v by dou y square is the right answer. So which is given by option A. So answer is option A. And for question 14, for a Newtonian fluid, sigma yy is given by option A, half mu times of dou u I by dou xj plus dou u j by dou xi. B, half mu times dou u by dou I plus dou v by dou x. Actually both are similar. And C, it is mu times dou v by dou y. And option D, it is none of the above. Answer to this is none of the above, because for a Newtonian fluid we will be having 2 times of mu dou v by dou y is the sigma yy term. And option D is none of the above is the right answer. We are going to question 15. In question 15, we have which of the following statements is true about the use of finite difference approximation for solving CFD problems. Finite difference approximations can be applied to problems described in cylindrical coordinate system. Finite, for a given partial differential equation, there is only one correct FD approximation. Statement 3, it is about finite different approximation at a point converts a partial differential equation into algebraic equation. And we have options. Options are option A, 1 only. Option B, 1 and 2. Option C, it is 1 and 3. Option D, it is 1, 2 and 3. So our main motto in CFD is we are writing the governing equations for solving the flow or whatever thing we are concerned in that particular domain. So that particular domain we would be discretizing it, the geometry. So we are having small cells. So why do we go for it? Because we are converting the partial differential equations, which is which we can't solve, into the algebraic equations for each particular grids. So in finite difference approximation, we are using the grids and we are solving at each grid points. We are discretizing using the each grid points. So which of the following statement is true about the use of finite difference approximation? So we need to identify which of the given 3 statements are right. The first statement, it is mentioned that FD approximation can be applied to problems described in cylindrical coordinate system. So can FD approximation be used in cylindrical coordinate system? Yes, it can be used in cylindrical coordinate system as well. Maybe in different coordinates, that is r theta z. And for second statement, it is for a given partial differential equation PDE, there is only one correct FD approximation. This we have seen in last class also, not as a thing, but we have discretized a single equation by different FD approximations, right? For example, once we discretize using forward approach or central difference approach, depending on the thing needed and depending on the order of accuracy and depending on so many other factors, for a given partial differential equation, there can be so many correct FD approximations. So statement 2 is false. Statement 1 is true, statement 2 is false. Statement 3, it is mentioned that FD approximation at a given point converts a partial differential equation into an algebraic equation. This is true because we have the main motto is converting a PDE into an algebraic equation which we can be solved using the numerical approach. So 1 and 3 are only right. Option A it is wrong, false. Option B is again false because it is mentioning 2. Option C is the right answer because it is given 1 and 3 only. Option D it is again false because it is including 2. Option C is the right answer, 1 and 3, because 1 is stating it can be applied to problems involving described in cylindrical coordinate system, and statement 3 it is FD approximation at a point converts a partial differential equation into an algebraic equation. Both are true. We'll go to question 16. In question 16 it is mentioned that which of the following statements is true about the use of finite difference approximations for solving a given partial differential equations. So there are a set of statements we need to identify which is true regarding the use of finite difference approach for solving a partial differential equation. Option 1 it is FD approximation of PDE is applied at all grid points. Option 2 it is same FD approximation must be applied at all grid points in a domain. Okay. Two statements are given. It is FD approximation of the PDE is applied at all grid points, and second is same FD approximation must be applied at all points in a domain. So first statement, coming back to the first statement, it is that FD approximation is applied at all grid points. It is false because we would not be using it in the boundaries also. I mean, those points would be including the boundaries, but in boundaries we would be having boundary conditions. So FD approximation of the PDE is not applied at all the grid points. Only at the required points we would be applying, because and then those like number of points and the number of equations, all those things also come into picture. And second statement is same FD approximation must be applied at all points in a domain. Again, this is false. Depending on the domain, it is not. If it is a simple one or if it is a complex one, all those factors come into picture, and we need not apply we need not apply the same FD approximation at all points. Different things can be used. Like for example, in a single equation itself, there would be a forward difference in one side and backward difference in the other side. So it need not be the same FD approximation at all points in a domain. So both the statements are false. So option A it is 1 only, it is false. Option B it is 2 only, again it is false. Option C it is 1 and 2, again it is false. Option D it is neither 1 nor 2, which is the right answer. Because first statement is also false, second statement is also false. So right answer is neither 1 nor 2 is the right answer. Option D is the right answer. We'll go to question 17. In question 17, it is asked that consider the Laplace equation in a two-dimensional rectangular domain with Dirichlet boundary conditions. The equation is discretized at all interior grid points using second order accurate finite difference approximation with uniform grid spacing in both directions. Which of the following statement is true about the resulting set of algebraic equations? So what we have a two-dimensional rectangular domain where with Dirichlet boundary conditions we are applying. So we are using some direct, this particular variable value is equal to this type of boundary condition. An equation is discretized at all interior grid points. So in all the interior grid points we have discretized the equations by using a second order accurate finite difference approximation, and it is given that grid spacing is uniform. For example, if the grid size is 2 and the next grid size is again 2, with uniform grid sizing is spacing in both directions, like 2 cross 2 cells in all the directions or 3 cross 3, and depending on it, uniform grid spacing in both the directions. Which of the following statement is true regarding the algebraic equation? So after discretization, we will be having a set of algebraic equations. So which one is true? Each algebraic equations will have exactly 5 non-zero coefficients. Each algebraic equations will have at most 5 non-zero coefficients. There will be at least one equation with only one non-zero coefficient. Actually, on looking at it, we can say that if we are using second order accurate finite difference approximation, almost we'll be having with the 5 non-zero coefficients at the max. The points near the boundaries and all would be having some values. So the non-zero coefficients would be vanishing. So it need not be that all 5 non-zero coefficients would be present. So but at the max it can have 5 non-zero coefficients. So second statement is right, first statement is false, and third statement there will be at least one equation with only one non-zero coefficient. Again it cannot be the true. One non-zero coefficient in a equation is not possible, because that would be giving out a direct equation, direct solution. So second statement is the only right statement. Option A it is 1 only, false. Option B it is 2 only, false. Option C it is 3 only, false. Option D it is, sorry. Option B is right because at most 5 non-zero coefficients. So option B is the right answer. 2 only is the right answer. B is the right answer. 1, 2 and 3 is false because 2 is only right, 1 and 3 are false. So answer is option B. For example, looking more detail into it, consider this as the rectangular domain, a part of the rectangular domain. Laplace equation in a 2D rectangular domain with Dirichlet boundary conditions. So this is the Laplace equation in a 2D domain. Dou square u by dou x square plus dou square u by dou y square is equal to 0. So we are discretizing it into these points like this. So I minus 1, I plus 1. So we are going with plus 1 plus 1 in the x spacing. Y again it is plus 1 plus 1. J plus 1, j minus 1. So consider we are discretizing the equation in this particular point. So what do we have? U at I comma j. So we have u I plus 1 comma j minus 2 u I comma j plus u I minus 1 j divided by delta x square plus u I j plus 1 minus 2 u I j plus u I j minus 1 by delta y square. So on looking at this equation, how many coefficients you would be having? 1, and this and that would be constituting 1, 2 and 3, 4, 5. This is having at most 5. But consider this is the boundary point. So we know the value of this. So u I minus 1 j would be known value. So it would not be constituting there. So that would be less 1. 5 minus 1 it would be 4. So it can have the utmost 5 values, but it cannot have exactly, we can't say all the equations will have exactly 5. Some equations will have 5, some equations will have less than 5. So we can say it as will have at most 5 non-zero coefficients. So statement 2 is the right, B is the right answer. Now we'll go to question 18. In question 18, it is mentioned that which of the following statements is true about the Gauss-Seidel iterative method for the solution of algebraic equations resulting from the discretization of linear Laplace equations. So in the previous slide, we have discretized the linear Laplace equation. So similarly, we will be discretizing it at all the points. So we'll be left out with that many points, and we need to find out the values of the variables at that many points. So we would be going with some numerical methods approach to get the solution. So at that time, if we are using Gauss-Seidel, which is an iterative method, what would be the statements that is true regarding the use of the Gauss-Seidel method when we are discretizing the linear Laplace equation? So statement 1 is that Gauss-Seidel method is the only method that can be used, and Gauss-Seidel method is the best of the available methods. So there are so many methods to solve the discretized equations. In that case, option 1 is false, because it is what it is stating. It is stating that Gauss-Seidel method is the only method that can be used. It is false because there are so many methods that can be used apart from the Gauss seidel method. Like uh, from the numerical methods, we can use whatever it is required, whatever it is applicable in that particular case we can use. So Gauss seidel method is not the only one that can be used. So option 1 is false. Option 2 is mentioned that Gauss seidel method is the best of the available methods. That can also not be said, because like so many other methods would be there, and it is not the best of the available methods. There are other better methods also available from the numerical techniques. So it all comes down to what we require at that particular problem and at that particular thing. So it is like both the statements are false. We'll see the options given. Option A, it is 1 only. Option B, it is 2 only. Option C, it is 1 and 2. Option D, it is neither 1 nor 2. Since both the statements are wrong, we have to go with option D, that is neither 1 nor 2. Option D is the right answer. We'll go to question 19. I think this is the last question of this session. Question 19, you wish to solve for a set of linear algebraic equations written in the form of Ax is equal to b using the Gauss seidel method. Which of the following you should have in your computer program? Check for diagonal dominance, stopping criteria, iteration count. 1 and 2 only, option A. Option B, 1 and 3 only. Option C, 2 and 3 only. Option D, 1, 2 and 3. Option D is the right answer, because what is the Gauss seidel method? It is an iterative technique where we are using it to solve for the variables in the method. I mean variables in that particular set of algebraic equations. So it is the we'll be getting an unknown from the first unknown. Like from the current iteration, it is like we will be going step by step. So it would be, we need to solve it simultaneously. I mean iteratively, sorry. We need to be solving it iteratively. So in this Ax is equal to b, like those types of equations we will be solving. So Gauss seidel, when we are using, we need to have a criteria for diagonal dominance. That is true. And for me, like since it is going in iteration, it would be going in loop. So we should have some stopping criteria, like if the tolerance or the value is less than this particular limit, then the iterative loop can stop. So and also we need to know how many iterations it has run. So iteration count, it also need to be included in the algorithm. So in our computer program, what we would be having, we would be starting with iteration. We would be first checking whether the diagonal dominance condition is satisfied, and then we will be having the stopping criteria. Like if the error is less than this, we can, like between these two iterations, if the error is less than this, we can stop this, or if it is not, we can go another loop like that. And iteration count, again we would be requiring to just know how far it has proceeded. So the which of the following you should have in your computer program? All three statements should be included, 1, 2 and 3. So answer to this is option D, 1, 2 and 3 is the right answer. So these are the problems for this week session. So if you have any doubts, you can ask now. Like from this week problem, if there is any doubt, please ask. In today's problem, mostly we have seen about the flow through a triangular duct session. So I'll just give a quick recap and then we can have doubts clearance. So if not, we can, yeah, we'll see after that. So these are the three cases we have seen, and it was about governing equations in few problems that I would skip for now, because I think we can go by this way. Governing equations, which we would be skipping, because we know, we right now I hope we are clear with that. And the new thing we saw is the solution or how many algebraic equations we need to solve, like how we have discretized the equations, for the cells. So by using the finite volume method. So finite volume method, two things we require. One is direction cosines, outward normal for each side, and gradients are evaluated at midpoints of each side. And those of the neighboring cells are boundary conditions. So these are things. And in this particular notes, I haven't included the L length of that particular side. So it should have come, and just please make sure you are including while making out, but it doesn't affect the questions answer in this because we are not solving for anything directly. And centroid we have found out initially for all those cells, and from the centroid I'll go by this way because my system is kind of hanging. So from the centroid, we have calculated the for each side we have calculated the gradient dou w by dou x or dou w by dou y. Because why are we going with w? Because it is in the triangle is in xy plane and flow is in z direction or w. So we are going with w, and we are using the direction cosine of that particular side -1 and 0 or something. For everything we have calculated, and for each cell we have done. This is square cell, and for similarly we have done calculation for the rectangular cell. For rectangular the centroid is different, and also while doing so we have implemented the wall boundary conditions, because we are taking between two cells. For example, when calculating from this side to this side we are using two cells, whereas when calculating from this side to this side gradient we are stopping at the boundary, because boundary condition is given as 0. The velocity at the wall is given as 0, so we are stopping at here. Whereas when going from this side to this side, that is this side, we are taking W1 and W2. Similarly for W2 and 3 sides, we are having W2 minus W3. And for this side, what are we having? We are taking the midpoint of this particular side, that is would be coming out 7, 1, and we are calculating from this point to this point, that is centroid is around 6.67, 0.67 or so, and from there we are calculating to 7, 1. Again, we know the value as W4 minus 0 because wall boundary condition is 0. Similarly, we have discretized all the equations, and we have written the equation. The coefficients would be different, I would say, because I haven't included the length of the side. It's just a mistake in the part. And after that, we have found out we have 10 equations, and what type of structure it was forming. It was not forming any diagonal structure, rather only main diagonal was available. That was one question. And how many non-zero coefficients, with how many rows having exactly 3 non-zero coefficients, that we have found out for us 3. And equations can be ordered in such a way that diagonal dominance conditions can be satisfied. Only after that we can proceed to getting the solution of that particular system. So in this particular case also we found out how diagonal dominance condition can be applied and it can be satisfied. And this is regarding finding the direction cosine of the vertical side, which we have found out -1, 0. And here we have found out for the diagonal side for this next cell. We have for the diagonal, the outward normal is in this in that direction, and we are resolving it into nx and ny components, and we are finding the diagonal value, diagonal length, and then we are finding the direction cosines. And similar problem, and where this was asked in how many cells we are not applying the boundary condition, and for FD approximation and Newtonian fluids, and these are all regarding the governing equations. And this is for some theory questions regarding finite difference. I think by now we should be doing. Why are we going with finite difference? Because we are discretizing the partial differential equations into an algebraic form, which would be solvable, and there can be various methods that can be applied, and so it is easier to get the solution for the system. And again, it is regarding the number of solutions, so number of non-zero coefficients. Since we are going with the second order, we are dealing with only these many adjacent points. It depends on the order. Here we have given it is the second order accurate, so we are going with only these many points. and it is in a 2D rectangular domain with digital boundary condition. So at the maximum we can have 5 points, whereas if boundary condition and all is applied and 1 point vanishes, it can be less than 5 or it can be 4. It can be 4 if both of them are lying near the walls. So it all depends. And it was about Gauss-Seidel method is like that is one of the method, and that is one of the technique. So where so many methods are also available which can give better solutions also depending on our requirement. We go with it. And in Gauss-Seidel method, what is we doing? We check for diagonal dominance. We use stopping criteria, and we also find out how many iteration count it has passed. Like sometimes it should not be going on in loop and all, right? So that can also sometimes be given as criteria in exceptional cases. So these are the content for this week. So I hope it is clear. If not, please ask questions. We can clear that as well. Mm, or else that is for today's session. We'll see. Somewhat was Mayank was asking doubts. Like we can discuss.
Yes, ma'am. I was asking the doubt, ma'am.
We can discuss after. Like if there are no doubts from other session, we can discuss. Just wait for a few minutes. We'll discuss.
Yes, ma'am. Yes, ma'am.
I think there was. Yeah. Thank you. Okay, I think everyone has left. I'll just stop the recording and then we can ask.
Yes, ma'am.